Hey everyone, welcome back to Calculus 1. This will be the 16th lecture of our course. And in this lecture we're going to discuss the second derivative test. So we just got done with the first derivative test in the previous lecture, so it makes sense we're going to jump into the second one right away. In the first derivative test, we kind of developed a couple of theorems, but the actual first derivative test theorem basically gave us criteria for identifying relative max and relative mins using just the positiveness or the negativeness of the derivatives and the sort of patterns that can exist. And so with the second derivative test, we're going to do something similar, but here we're going to use naturally the second derivative rather than the first derivative. So let's jump into it. So we'll call this section 3.4 the second derivative test. Okay. All right, so let's start with a definition of. So the second derivative test is kind of deals with the idea of concavity. So let's flush out. I mean, some people may know when you hear that word concavity, concave up, concave down. You may have some inclination as to what that means exactly. But let's work out a definition for what we mean in this context. Okay, so let f be a differentiable function on an open interval on what is called I. Okay, so the graph of f is concave upward on I if f prime is increasing on the interval and concave down word on I if f prime is decreasing on the interval. Okay, all right. Okay, so let's read through that one more time here. So let f be a differentiable function on an open interval I. Simple. The graph of f is concave upward, okay, on I if f prime, the first derivative of f, is increasing on the interval. And it's concave downward on I if f prime, the first derivative of f, is decreasing on the interval. Okay, all right, so let's take an example here. Let's take a look at an example and see what's happening here. So we're going to consider the function f of x equals 1/3 x cubed minus x. Okay, now the derivative of this function is x squared, so it's 1/3 times 3x squared, and then it'd just be minus 1. Okay, let's plot this. I'm going to try to give you a nice picture of what this looks like, because I think some of these relationships are easiest if you just can see a picture. It can help you to get a good sense for this. Okay, so we're going to plot f first. And so let's see, we'll make this 1, 2, 3, 1, 2, 3. So this would be like 1, 2, 3, negative 1, negative 2, negative 3. And we'll do the same thing up here. Okay. And then down here as well. So negative 1, negative 2, negative 3. Okay. Okay, so this first guy comes through right here, and then it goes through there, and then it comes down. Where is that about? So somewhere-ish around here. This isn't perfect, but that's okay. So, well, hold on, I did that wrong. So this should be here, actually. Okay, so the function kind of comes up to here, and then it goes down like that, and then it does one of these. Okay, something like that. So that's f of x. Okay. Now, the derivative, we can see here that the derivative is a quadratic function, just with a minus 1 on the end there. So that just means it's kind of shifted down, right? So it's going to cut through here. And I believe it's also going to cut through here and through there, right? So it will look like this. Okay. So this is f prime of x. All right. So what the definition of concavity says is that a function, the function f, is concave up wherever on an interval if f prime is increasing on the interval, right? And so, and it's concave down wherever f prime is increasing. Okay, right? So let's look at, so f prime is this guy back here. Let me make it a little darker. It'd be nice if I had multiple colors, but I don't. Okay, so the derivative will make, because that's kind of the thing that we're most interested in, right? So the derivative here, so basically from like here, you know, over this direction, we say that f prime is decreasing, right? Okay, so all throughout this region, f prime is decreasing. And similarly over here, we'd say f prime is increasing. Right, so you can see that, right? See how it's increasing here and it's decreasing here. Okay, so it's decreasing and then it hits this minimum and then it starts to increase. Now, what's useful to do is to take a look at this and to see where do the interesting points lie here. So now the okay, so this part over here, this would be, so here where we can see the derivative decreasing, this is where we have this shape that looks like it's concave down, right? So we can see here how the function f itself is concave down here, right? So just put that down here. So f is concave down on this side. Okay. Now over here, here's where we see the derivative is increasing, right? So it starts down at this minimum here, and it kind of is, you know, it's obviously increasing throughout this whole region. And that's where we see this part over here, where the original function has sort of a concave upward view appearance. So here f is concave upward. Okay, right? And then right in the middle, right here where we have this minimum, right? You can see we have this minimum on the derivative function. This guy here is called, and we'll get to this more in a few moments, but this is where the concavity shifts. So here you have concave down, and then you hit this point, and it becomes concave up. This is what's called an inflection point. Okay, right? So this is an inflection point. Okay. All right. So we're just kind of trying to get comfortable with some of these ideas, and we'll get into them in a little more detail in a moment. You know, kind of what all of these things mean. But this is just an illustration of this idea of concavity and how the original function f, you know, this cubic polynomial here, how that function relates to its derivative, and specifically with respect to the idea of concavity. Okay, so when we say concave up, what we mean is something that's like this, right? Okay. Right, so this part here is where you have the concave up. Okay, and when we say concave down, that's when the function looks like this. Now, however you want to remember that. I mean, to me, it's not hard to remember this, but some people would find this kind of like, oh, how do I remember that? So concave up would be like, like a bowl or something that would catch something. Concave down is more like a hill, where things are going to roll off of it. Okay. Okay, so that is the idea. So basically, kind of what's coming next would be the idea of being able to find intervals on which a function is concave up or down is going to basically boil down to identifying intervals on which the derivative is increasing or decreasing, right? So similar to our previous section, so being able to identify intervals where concavity is up or down, right? Being able to identify intervals where concavity is up or down is going to boil down to identifying intervals where f prime is less than 0 or f prime is greater than 0. Okay, so basically it's very, very similar to our previous work on the first derivative test. And so let's jump into kind of a preliminary theorem, and then we'll get to the second derivative test, the actual theorem. Okay, so let f be a function whose second derivative exists whose second derivative exists on an open interval I. Okay, so similar to our previous section where we said, hey, let's let f be a function that's differentiable, right? So here, what we're really going to be interested in is the second derivative. And so here what we're saying is let f be a function that's not only differentiable, but also whose derivative is differentiable, i.e. where the second derivative exists. Okay, now so let f be a function with a second derivative, then here's what we can say. If f double prime of x is greater than 0 for all x in I, okay, then the graph of f is concave upward in I, right? Okay, so this kind of just basically take the definition and toss it into theorem form, right? So this follows directly from the definition. So if f double prime of x is less than 0 for all x in I, then the graph of f is concave down in I. Okay, so those are the two options. Okay, and then of course if the second derivative is equal to 0, then it's neither of these. Okay, so these are exclusive here. Okay, so let's take a look at an example here and use this theorem in an example. Okay, so determine the open intervals on which the graph of, so f of x equals e to the negative x squared over 2. Okay, here's our function. We want to determine the open intervals on which this function is concave up or down. So find where f is concave up or concave down. Okay, that's what we're after. Okay, so we're going to need the first derivative and we're going to need the second derivative. So let's calculate the first derivative here first of all. And this is just a chain rule, right? You've got the outer function, which you can think of as e to the u, and then u is equal to negative x squared over 2. And so we can do this in a quick one step. So e to the u, when you differentiate that, we just get e to the u, so nothing changes. And then it'd be times the derivative of u, which would be negative 2x over 2. Right, and so this would all amount to negative x e to the negative x squared over 2. That's the first derivative. Okay, sounds good. The second derivative would be the derivative of the first derivative, right? So to do that, now we notice this, this derivative got a little more complex as we differentiated the first time. So now we've got a product rule scenario. Right, so we're going to have to differentiate this using the product rule. And so we'll go, I'll just write it out first, negative x, and then it's dx of e to the negative x squared over 2. And then it's plus dx of negative x times e to the negative x squared over 2. Okay, so just kind of writing it out to start with. And we can crank this out real quick. So it'll be negative x, and then basically this derivative is just the same thing as what we just did, right? So that would be negative x e to the negative x squared over 2. And then here, this is just negative 1. So it'll be plus negative 1 e to the negative x squared over 2. Okay, we can clean this up a fair amount. So this would be like x squared e to the negative x squared over 2 minus e to the negative x squared over 2. And I think probably the best thing to do would be to pull the e to the negative x squared over 2 out and kind of do a little factoring here. Like that. And then you're left with x squared minus 1. And that might be the best way to write it. We'll see. Okay. All right. So that's the first and second derivative. And now in order to find those intervals, we need to know where all of the critical values, or the, I guess, critical numbers, however you want to say it, critical numbers, critical values, we need to know where those are, but this time with respect to the first derivative, right? And so what we need to look at then are all of the places where the second derivative is equal to 0. Okay, and so we got to set the second derivative equal to 0 and solve for x. So e to the negative x squared over 2 times x squared minus 1, set that equal to 0. And you can quickly divide this guy out, and you'll see that x squared minus 1 equals 0 is what you're left with. And so that means x squared equals 1. And so we've got critical values at x equals plus or minus 1. Okay, so critical values here. Okay, no problem. All right, and then just like before, let's go ahead and set up our ranges to look at. Okay, so we'll have basically everywhere that x is less than 1, or sorry, less than negative 1 first, and then everywhere where x is between negative 1 and 1, and then everywhere that x is greater than 1. Right, so these are the regions of interest here. These are the, basically you've got x equals negative 1 here, x equals positive 1 there, and then these represent the intervals between those, between and around those numbers. Okay, now what we'd want to do here is just plug in the second derivative, plug in test values from each region into the second derivative. So we could test x equals negative 2 here. We could test x equals 0 here. And we could test x equals positive 2 here, right? So when we plug all of those values in, right, we would plug in f double prime of negative 2. Okay, and that just means you're going to take that negative 2 and you're going to plug it into this function. Okay, now in the interest of kind of keeping my table concise here, I'll just tell you that your result here is going to be a positive value. Okay, so you can do that on your own, but when you plug a -2 in here, you'll get 4 minus 1, so you get a 3 here, and then this is a positive value as well. And so you get a positive value. Now what happens when you plug it in here, right, when you plug in 0? Well, when you plug in 0, you get a negative value, okay? And then when you plug in +2 into the second derivative, here you get a positive value as well, okay? So you can confirm that on your own. Just pause the video, plug -2, 0, and 2 into this function, and confirm that you do in fact get positive, negative, positive. And so what does that mean? Well, wherever you've got second derivative greater than 0, positive second derivative, that's going to mean you have a concave upward region. Here you're going to have a concave downward region. And then over here, you're going to have a concave upward region as well. Okay, so you got upward, downward, upward. Okay. And so that is the information that you're going to need to answer the question, basically. So we're asked, recall, to find where f is concave up and or down, up or down. Right? So we could say f is concave up on the intervals, what, -infinity up to -1, and 1 to +infinity. F is concave down on the interval from -1 to 1. Okay? Perfect. All right, very good. So that's the idea. Let's do another example. Let's try another example here. And for this one, let's do the same thing. Let's find the open intervals in which the graph is concave up or down for the function f of x equals x squared plus 1 over x squared minus 4. Okay. And so we can do this, no problem. We're going to have to find the first derivative and the second derivative here. So the first derivative is going to be a quotient rule. So it's low d high minus high d low. So it'll be x squared minus 4 times d dx of x squared plus 1 minus x squared plus 1 d dx of x squared minus 4, all divided by x squared minus 4 squared. Okay, so that's the first derivative. Of course, we have to actually calculate it now. We get x squared minus 4 here, and then this will just be a 2x minus x squared plus 1, and then this is just a 2x. Okay, so that's nice. And then you've got x squared minus 4 squared in the denominator. Now we can expand this, and we'll get 2x cubed minus 8x. That's this part. And then minus 2x cubed minus 2x. Okay, and then that's all still over x squared minus 4, quantity squared. And the 2x cubes cancel out. And so it looks like you get like minus 10x here. Okay, all over x squared minus 4, quantity squared. Okay, so that's the first derivative right here. That's our first derivative. Now we're going to need the second derivative as well. Okay, and so the second derivative, okay, so that's the derivative of this guy, and again, the quotient rule here, so low d high minus high d low. So you have x squared minus 4 quantity squared, and then I'm just going to do it in a one step here. It'll be minus times negative 10, and then it'll be minus negative 10 x, and then this the derivative of this denominator, it's going to be like 2x squared minus 4, right? So that'd be like 2u squared, right? So it'd be 2u. And then times the derivative of that inside would just be 2x. Okay, and then that whole thing over x squared minus 4. But now instead of being the second power, it's to the fourth power because you have to square it again. Okay. Then cleaning this up a little bit, we can, sort of rewrite this. So negative 10x squared minus 4 quantity squared. And then what happens over here? Over here you would get, let's see, so you got 2, 2, and 10. So that's a plus 40x. And then times x squared minus 4 all over x squared minus 4 to the fourth power. And let's see here. So the next thing to do would be do some cancellation here. We can cancel an x squared minus 4 out of all three of these. And so we would have negative 10, and then this would be x squared minus 4, first power now. And then this would be plus 40x, right? And then this would just become a 1, and then that's divided by x squared minus 4 to the third power. Okay. And now I think we'll have to expand this numerator and and combine terms. So negative 10x squared plus 40, and then plus 40x squared. This should be an x squared. X. There we go. All divided by x squared minus 4 third power. And finally, I think this will be it. We would just run a right. So these two would combine to give us a 30. Well, let's do it in two steps here. So you get a 30x squared plus 40 divided by x squared minus 4 cubed. So that's a 3. And then we can factor the 10 out here, I guess. We could do that. So 10, and then it would be 3x squared plus 4. Okay. Kind of a complicated function to differentiate twice. But here we go. So this would be our second derivative, right? So we got the first derivative up here, and then the second derivative is what we just did. All right. So now we need to know those critical values. So we need to know where the second derivative is equal to 0. So f double prime of x equals 0 to solve for x, right? And so that means setting this guy equal to 0. 10 times 3x squared plus 4 over x squared minus 4 cubed equals 0 is what we have to deal with. Now, again, don't get stressed out about this. The fact that it's 0 on one side means it's very easy to get rid of a lot of this junk. So multiply both sides by x squared minus 4 all to the third power divided by 10, and you can basically get rid of this guy, and you can get rid of the denominator. And so you have 3x squared plus 4 equals 0. Okay. Then, let's see here. So that means we would have, so if we solve all of that, that's going to imply that x is equal to plus or minus 2, okay? So when we get down to here, so here are our critical values. Okay. Now, how did we, right, so, so hopefully this is clear how we can get there, right? So plus or minus 2 are our critical numbers. Okay. Then we have to build out our normal range here, right? So we've got x less than negative 2, this section here. And then in the middle, we've got negative 2 up to positive 2. And then everything above that, right? X greater than 2. Okay, so here's our regions. Okay, and so obviously x negative 2 is kind of the dividing point here, and then x equals positive 2 is the cutoff point for this middle to upper region. And then it's just a matter of identifying test values in each region and testing them. Okay, so here we'd want to test, let's see, we could pick any value less than -2, probably -3 would be good. Here we want to test any value between there, so obviously x equals 0 is ideal. And then up here, test x equals +3. And then all you have to do is just plug all of that into the second derivative. And so you'd see that it's greater than 0 here, less than 0 there, and then up here it is greater than 0 as well. So we're concave up, concave down, and concave up. Okay. So this function is interesting. I'm going to draw it on here. So here's your x-axis, and here's your y-axis. So I've got these are these are going to be asymptotes here, so you can kind of think of those as dashed lines. Okay, so in the middle here, it kind of comes up like this. Looks a bit like that. And then over here, it looks like this. Right? It kind of comes up against these asymptotic values. Right? These asymptotes here. Okay, so in the middle, it's concave down, right? It's mounded. Over here, it's concave up, as with over here. Okay? So that's what this function looks like. Okay, and then you can see naturally that you do have these asymptotes, because what was the original function? The original function was f of x equals x squared plus 1 over x squared minus 4. So obviously x squared minus 4 equals 0 implies x equals plus or minus 2. So that's why, so if this was -1, this would be -2, this would be +1, and this would be +2. And so that's where you're getting these asymptotes at these plus and minus 2 values. Okay, so that's another example of kind of using this theorem to talk about concavity. Okay, so the next thing on for this section is this idea of inflection points. So basically the points on the graph where the concavity changes is called a point of inflection, right? So the points on a graph where the concavity changes, okay, are called points of inflection. Or inflection points, however you want to phrase it. But I've heard it both ways, so obviously it's fine. So a couple of examples. Let's take some examples of just kind of what this looks like. Okay, so you could have something like this, which is kind of like the first example we saw, right? And so the point of inflection is right about here, somewhere like that, right? And here's where you're going to be up, and here's where you're going to be down. Okay, the inflection point is right in the middle of those two regions. Okay, another example of kind of what these can look like would be something like this. Maybe the graph comes up, flattens out, and then goes up more. Right, and so right there in the middle, you might have is where you would have an inflection point, because over here the concavity is down, and over here the concavity is up. All right, it's a little hard sometimes to kind of see all of this, but yeah, the idea here is that this is, well, technically speaking, this would be where the second derivative is negative over here, and the second derivative is positive over here. But you can kind of see it in the graph, right? The sort of the shape of the function is different. And then another example of what these could look like might be something like this, where it kind of comes up like this, and then it sort of goes near vertical, but not quite, and then it turns off that way. And so over here you would have an up, your inflection point's right in the middle, and then it'd be down on the other side. All right, so it's important to note that these are functions, right? So this doesn't actually turn, strictly speaking, vertical. It just kind of looks like it in my drawing. But this would pass the vertical line test and everything. So these are some examples of how inflection points can manifest in your graphs. Okay, very good. So that's kind of the intuition behind an inflection point. Now let's talk about like what really is an inflection point. And so theorem. So if C comma f of C, right? So this is an ordered pair, the x equals C, and then f evaluate at C. So if this ordered pair is a point of inflection, so if this is a point of inflection of the graph f, okay, then either f double prime of C is 0, or f double prime of C does not exist. Okay. All right. So perfect. This fits very well with the idea of maximums and minimums, right? So we saw something similar with the first derivative, right, where we said you're going to have maxes and mins where relative max and mins wherever the first derivative is equal to 0, or where the first derivative is possibly does not exist, right, wherever f is not differentiable. And so it's exactly the same story here, except instead of relative max and min, we're now talking about points of inflection, and instead of the first derivative, we're talking about second derivative. Okay, so very similar though to the problems that we've seen previously. Let's take an example here, and this will be a simple one, but f of x equals x to the 4th minus 4x cubed. Okay, let's identify the inflection points. The inflection points, okay? So the first derivative is 4x cubed minus 12x squared. And the second derivative is 12x squared minus 24x. Okay, so based on the previous theorem, the inflection points are going to occur. So we can see, first of all, second derivative exists everywhere, right? This is just a quadratic equation. It's defined for all real numbers. There's no gaps in the domain of f double prime. So this piece of it here doesn't apply, right? So if we have inflection points, they're going to be found based on this part right here. So that means we have to set the second derivative equal to 0 and solve for x. And so doing that, we would have 12x squared minus 24x equals 0. And it looks like we can factor a 12x here out of both of these guys, and so you get x minus 12 equals 0. Okay. And, sorry, not x minus 12, x minus 2. That'll make a big difference. X minus 2 equals 0. And so one of our inflection points is at 0. So the 12x equals 0 implies x equals 0. There's one of our potential inflection points, or it is an inflection point. And the other one, x minus 2 equals 0, implies x equals 2. And there's the other one, right? So for those two, those are going to be our inflection points. And so we can do the usual thing with the range, right? We can plug in x less than 0, and then x between 0 and 2, and then x greater than 2, right? We can plug those values in, and when we do that, just kind of testing some values in the ranges, we would get the following. Okay, so all I've done here is just plugging in test values. -1 is in this range, 1 is in the middle range, 3 is in the upper range. Plug those all into the second derivative, and you would see that you're up here, you're down here, and then you're up there. Okay, so the inflection point theorem tells us that given an inflection point, that then either the second derivative is 0 at the point, or the second derivative does not exist at the point. So the reverse is not generally true, though. Okay, so we would have inflection points at x equals 0 and at x equals 2. Perfect. Okay, very good. Let's take a look at one more example here. So identify the points of inflection for f of x equals x to the 4th. Find the inflection points. Okay, so f prime of x equals 4x cubed. F double prime of x equals 12x squared. Okay. And so then f double prime of x equals 0 implies 12x squared equals 0 implies x equals 0. Okay, so here we have a candidate for an inflection point of x equals 0. So we can test everything less than 0 and everything greater than 0. Okay, and so just plugging values in here. If we plug in -1, right? If we plug in -1 to this function, we're going to get 12, which is obviously greater than 0. And if we plug in f double prime of 1, right, which is in this range, we're going to get the same thing, right? So here we're up, and here we're up as well. So here, and so in this example, we can see that, when x is 0, so what we can see is this. So in this case, f double prime of x equals 0 when x equals 0, right? But x equals 0 is not an inflection point. Of the function f of x equals x to the 4th, okay? So finding the roots of the second derivative doesn't automatically tell you the inflection point. You really have to test the regions to confirm that the concavity does in fact change. Okay, so you have to make sure that the concavity actually shifts from up to down or down to up at these points, right? And so here we see that doesn't happen, right? So the second derivative is positive in both regions, which just means that the concavity doesn't change here. Okay, all right, so let's get out the second derivative test. So in addition to concavity, right, the second derivative test can be used to perform a simple test for relative maximums and minimums. So it's going to give us information on the concavity, but it's also going to tell us something about maxes and mins as well. Okay, so let's talk about the second derivative test. Okay, and this will be the second derivative test. Okay, so let f be a function such that f prime of c equals 0 and f double prime exists on an open interval containing z. Okay. Okay, so let f be a function such that f prime of c is equal to 0 and f double prime exists on an open interval containing c. then first, if f double prime of c is greater than 0, then f of c is a relative min. Okay, and second, if f double prime of c is less than 0, then f of c is a relative max. Okay, and so, all right, so basically, the second derivative test is telling us, is giving us the criteria for relative mins and relative maxes. Okay, so what is being said here? So f is a function, and the derivative, the first derivative of f, is 0 at c. Okay, so if the first derivative is 0 at c, and the second derivative is at c is greater than 0, then you got a relative min there. If the first derivative is 0 at c, and the second derivative is less than 0, then you got a relative max. Okay. So let's prove this theorem, because I think this is another one that's fairly straightforward, but it's a good exercise in reading and writing proofs and thinking about proofs. So here's what we'll start with. So if f prime of c equals 0 and f double prime of c is greater than 0, then there exists an open interval. Okay, there exists an open interval I containing c, for which, okay, and for which what? Well, for which this f prime of x minus f prime of c divided by x minus c, right, is, now notice these are 0, right? So this guy's 0. This is going to be equal to f prime of x over x minus c, and that's greater than 0. Okay, so so basically, what are we saying here? So if the first derivative is 0 at c and the second derivative is greater than 0 at c, then there's going to exist some interval that contains z for which this following is true: f prime of x minus f prime of c over x minus c is equal to f prime of x over x minus c, and that's going to be greater than 0. Okay, and this would be true for all x in the interval, right? So for all x in I, wherever x is not equal to c, basically, right? So then, if x is less than c, right? If x is less than c, then x minus c will be less than 0, and f prime of x will be less than 0. Okay? If x is greater than c, okay, if x is greater than c, then x minus c would be greater than 0, and f prime of x will be greater than 0 as well, right? So again, we're just kind of looking at this interval here, looking at this equation or this inequality and using logic, right? So the derivative changes from negative to positive at c, and the first derivative test implies that f of c must be a relative minimum, basically, right? So to kind of sum it up, f prime of x changes from, negative to positive, right? See right here, from negative to positive, and it does that at c. Okay, and so if you go from a negative to a positive, that means your slope is coming down and then it's going up, right? Which means c is a relative minimum. Okay. Okay. All right, and so that's the one case. Now the other case would be where you would assume the reverse for the second derivative. You would assume that the second derivative is less than 0 at c. So the other case is similar. Well, it's the same, basically. I mean, you just flip some of the inequalities, but all of the logic and the approach is going to be the same. Okay. Basically going to follow the same follow the same template. Okay, let's do an example using this and see how this comes into play here. So for this example, we want to, so given this function f of x equals negative 3x to the 5th plus 5x cubed, find the relative extrema. Okay. So we need the first and second derivative, and I guess implicit here is to find the relative extrema using the first and second derivatives. so f prime of x, or using the second derivative. So f prime of x is equal to, now we can differentiate this quickly, negative 15x to the 4th plus 15x squared. And so if we set f prime of x equal to 0, then that means you've got what, basically, let's factor a negative 15 out of here. Let's factor out positive 15x squared, and then you would get what, negative x squared plus 1, so we'll just write 1 minus x squared here, equals 0. Sorry, I kind of two-stepped there. But, so then we can quickly identify the roots here. So you're going to have a root 15x squared equals 0. So basically x squared equals 0. So x equals 0. Technically, this would be like a repeated root. So there should be two roots, right? Because this is a 4th degree polynomial, so there should be two roots. So you have a repeated root here, and then the other one comes from this. And so x squared equals 1, x equals plus or minus 1. So it'd be the plus or minus the square root of 1 equals plus or minus 1. Okay, so you'd have that one. And so you'd have three roots of f prime, and they are negative 1, 0, and positive 1. Okay. Okay, so then what we can do, so what we could do here, now that we know where these critical numbers exist, or we know these critical values, we could go in and use the first derivative test to say, okay, let's test the values in each of the intervals, right? So let's go test f prime of negative 2. Let's test f prime negative 1/2. But using the second derivative test, we can do this more efficiently, right? We can just plug these three values into the second derivative. So the second derivative of x is going to be the derivative of this, which is what, negative 60x cubed plus 30x. Right, let's just plug in those values. So f double prime of negative 1. Well, that's negative 60 times negative 1 cubed plus 30 times negative 1. Right, so you run those numbers through and you get something like 30, right? So this would be negative times a negative is positive, minus 30 is 30, so it's greater than 0. F double prime of 0, right? Well, you can see you're just going to plug in zeros here, so you get a 0. And f double prime of 1, right, will give you, so here, what are you going to get? Negative 60 times 1 plus 30 times 1. And so this would be negative 60 plus 30, so you're going to get a negative 30, right, which is obviously less than 0. Okay, so what does this look like? Well, when you plot this graph, okay, this will be kind of a decent picture, hopefully. So you're going to have a relative min down here at negative 1, and then at 0 you're going to have something going on there, and then you're going to have a relative max up here, right? So the function kind of comes down to this, and then it turns back around, and then it does this like little flattening out trick here, and then it comes up to here, and then it heads back down. Right, so this is what it looks like, and so Here you're going to have, you know, your relative min. Here you're going to have your relative max. And then in the middle you don't have either, right? You just have this, it's just an inflection point, isn't it? Right, so the concavity will change here, right? But the key here is that you could use the values here and here to identify these 2 points. So here's your min, right? The second derivative is greater than 0, right? So that gives you a relative min according to the second derivative test. And here the derivative is less than 0, so that's going to give you a relative max according to the second derivative test. Right, so you can just use that second derivative test to plug in directly. You can plug those the roots of the first derivative directly into the second derivative and identify your relative mins and maxes that way. Right, so it's just these interesting relationships between the derivatives, and the relationships go on, right? The third derivative tells you something about the second derivative and the first derivative, right? And so on and so forth, right? So, but I mean, for the purposes of curve sketching, we pretty much stop, right? But these derivatives tell us a great deal about the shape of the functions that we're studying. So that's the second derivative test, and I think we'll leave it off there. Next lecture we'll get into a quick discussion of what do limits at infinity look like. Okay, and so we'll talk through some of that, and also discuss, you know, some of the issues that can arise when you're evaluating limits at infinity. And then after that, we'll be totally ready to do curve sketching, like a summary of curve sketching. Right? And then that brings us very close to the end of the class. I think only one more lecture after that where we'll discuss some optimization problems, and then that'll be the end of Calculus 1. Okay, so we'll see you next time, and we'll discuss limits at infinity.